Hi, Dave Velasco here with Nortec, and today we're going to be doing a practical demonstration of the Doppler effect, which is what ADCPs use to measure water speed. Now, the Doppler effect is the apparent shift in frequency as a function of the relative motion between an observer and the source of a wave. In this case, the wave that we're going to be using will be the sound of the horn of this car, and the observer will be a stationary camera that is placed on the side of this road. So what we'll do in this demonstration is drive the car past the side of the road here, and we'll sound the horn continuously while the sound is being captured by the camera on the side of the road, and the recorded sound will contain the Doppler effect. So in addition to recording the sound from the side of the road, we're also going to be recording the sound from inside of the car. And this is to illustrate the fact that the Doppler effect has to do with the relative motion between the observer and the source. Okay, before we get started, we need to make one minor adjustment. Well, it turns out that horns in cars actually have two frequencies, not just one. And this kind of messes things up when we're trying to actually detect a Doppler shift. So what we need to do is open up the hood, and we're going to disconnect one of the horns. So let's go. Okay, so what we're going to have to do is just disconnect the horn in here. So it goes from sounding like this to sounding like this. Okay, so here we go. We are going to accelerate the car to 50 miles per hour. And then as I approach the stationary observer, I'm going to start sounding the horn. And then we hope to capture the Doppler effect. Let's see what we got. Okay, so now that we have recorded both inside and outside of the car, let's see what we capture. We're going to start by listening to the sound from inside of the car. And now let's listen to the sound from outside of the car. Let's take a closer look at these sounds. Here we have the waveform of the sound from inside the car. This sound has no Doppler effect because the source, that is the horn, was moving together with the observer, that is the microphone inside the car. So there's no relative motion between the two. Let's hear it again. So, no relative motion between the source and observer equals no Doppler effect. Here we also show a spectrum of the same sound, which is a way to visualize the sound as a function of how much energy is in each frequency band making up the total sound. The spectrum allows us to separate different parts of the sound. For example, this represents the background noise of the car itself. This peak corresponds to the frequency of the horn. And these other peaks are harmonic frequencies of the horn. The highest energy peak is at a frequency of 500 Hz, which is the horn's nominal operational frequency. Now, from the observer's perspective, there is a Doppler effect as there is relative motion between it and the source. Let's hear it again. And as with the first case, here we have the spectrum of the sound. But here we show two spectra, one taken just before the car reached the observer, so it was moving towards it, and another taken just after the car passed the observer, so it was moving away from it. Note that the two peaks in the middle of the graph are at different frequencies, one higher and another lower. This difference is the Doppler effect. If we also plot the spectrum from the source, we see that it lies in between the two peaks of the recorded sound. By zooming into these peaks, we note the source frequency is the 500 Hz we had already determined, while the frequency when the car was moving toward the observer is higher at 530 Hz, and when it was moving away, it was lower at 470 Hz. With these frequencies, we can use this equation to estimate the speed of the car. C represents the speed of sound in air, which is approximately 340 meters per second. FD is the difference between the two frequencies, which we also divide by 2 because the observer first hears the sound coming toward it and then again when moving away. If we run these numbers, we come up with 46 miles per hour or 73 kilometers per hour, which is approximately how fast the car was moving at that time. And there you go. This is how the Doppler effect is computed. Okay, thank you for watching. This concludes the demonstration of the Doppler effect. I would like to thank my colleague Jeremiah Ness for operating the camera, and thank you for watching the video. Thank you.